All right, let's try to understand this better now in a few different ways. One way you can try to understand something like that better is to pick a particular x, like x equals 3. If x equals 3, you do the exact same calculations as over there. What you'll get is this, right? But back over here, because if x is 3, 3 times 3 is 6. You get a 6 right there. You should check this after class that you do get the same thing that I have over here. And that will equal, that will simplify to this as long as delta x is non-zero. Okay? What am I really doing graphically here? Again, the function is f of x equals x squared. Your standard parabola. F of x equals x squared. And in this particular thing, I'm thinking about imagining x is 3. This would be 3 here, and that would be 9. And, okay, pretend delta x is something specific. Well, maybe I shouldn't pick a specific number, but just draw a specific distance here. Let's pretend that distance right there is delta x. So that number right there is 3 plus delta x. If I go up to the graph, and over here, this number right there is going to be f of 3 plus delta x. And by the way, f of 9 is f of 3. That's 9 right there. This is rise over run, change in y over change in x. Not for the curve itself, but for a line. What line? The line between this point and this point. This line right here. A line connecting 2 points on a curve has got a special name. It's called a secant. It's called a secant line. Right there. And this calculation that I just did gives you its slope. As long as delta x is something non-zero. Its slope is 6 plus delta x. So if delta x is 1, its slope is 7. If delta x is 2, its slope is 8. Well, if delta x is 1, then this number is going to be 4. And this number is going to be 16, 4 squared. 16 minus 9 is 7. Divided by 1, rise over run would be 7. This would be 7 when delta x is 1. But now I say, I want to let delta x go to 0. Even though these are only equal when delta x is non-zero. And if I let delta x go to 0 here for this thing, it goes to 6 plus 0. 6 as delta x goes to 0. So what I'm trying to say is, as delta x gets smaller and smaller, as this point here moves toward 3, this secant line becomes more and more like the tangent line to the graph at this point. And in the limit, we say it does become the tangent line. And the slope of that tangent line is going to be 6. But is it a problem that I'm letting delta x go to 0, even though I can't plug in delta x equals 0 there? Turns out it's not a problem. Essentially, the reason is this. If you were to graph this function as a function of delta x, this is kind of weird. Look at that expression and treat delta x as a variable. It would be the same as the graph of this function because they're equal as long as delta x is non-zero. And what's the graph of this one? It's got a slope of 1 and a vertical intercept of 6. It's a linear function of delta x. It looks like this. This will be negative 6 there. These are equal as long as delta x is non-zero. So what that means is if we were to graph this function here, there would be a hole in the graph right there. A point missing. But the graph still gets closer and closer to 6 as delta x gets closer and closer to 0. And that's what justifies doing this. I know that's a lot to think about in the span of 2 minutes. 3 minutes. We come back to things over and over again. you will see this again. It's key to understanding calculus. Here's some other graphs that can give you other perspectives on this, though these are animated and so it, well, okay. Graphs are on the next slide after this, okay. Let me quickly go through this one. This is essentially giving you details about what I just said, except for an arbitrary x. At the end of the last slide, what happens is we let delta x get smaller and smaller. In other words, approach 0. The limit as delta x goes to 0 of the average rate of change would equal 2x in the end. If we dot dot dots because there's missing work there. Let delta x go to 0 here in the end. That becomes 0 and you're left with 2x, which is 6 when x is 3.
Is 2 the slope of the tangent line?
2x is the slope of the
2x is the
tangent.
slope of the tangent.
So it's 6 when x is 3.
Oh, yeah, because it's
8 when x is 4,
yes.
yeah.
Okay.
What does this mean? For any given x like 3, exactly what I just said, the quantity 2x is the slope of the graph at that point. More precisely, it's the slope of its tangent line at that point. Not a secant line, but tangent. It's just touching your curve at one point. Tangent essentially means to kiss. So it's like the curve and this line are just kissing at that one point. Like that. Okay? That's what the word tangent means, literally. This 2x is called the derivative of f of x equals x squared at the input x. And it's denoted by f prime of x, and you can write f prime of x equals 2x for this example. And if x is 3, then that equals 6. And that 6 is the rate of change, the slope of the tangent. It's the rate of change of the graph of x squared at that moment in time. And if, imagine x is time and f of x is distance, if that's true, if x is time and f of x is distance, and this is your distance as a function of time, the 6 at time 3 is going to be your speed. And if the units for distance are meters and time in seconds, the 6 would be in 6 meters per second at that moment in time. What's called instantaneous speed. If you're driving a car and your car's speedometer is super accurate every moment of time, essentially, it would be whatever your speedometer says at that moment in time. 2x is a function as well, and it can be graphed. You can graph the derivative. Instead of saying let x equal 3, I could say let x be arbitrary, be a variable. And I could graph the derivative. It's a function of x. That's kind of wild to think about it too. And here are some graphs. I picked x equals 1.5 here. And essentially now we're visualizing what I was trying to draw over there. Except x is 1.5 instead of 3. 2x, the derivative, is 2 times 1.5 is 3 when x is 1.5. The slope of the tangent, which is going to occur when delta x is real close to 0, right about now, that slope is 2 times 1.5 or 3.
I'm sorry, I can't really see. What is the symbol next to the f?
It's a prime. F prime. Is that what you're talking about?
Yeah.
Yeah.
Okay.
Like that. An apostrophe kind of symbol, what we call it prime. The slope of that secant line, we are really mostly seeing the secant lines here. The slope of that is 2x plus delta x. It depends on not only x, but also delta x. You can see the slope is changing. As delta x is really getting smaller, going towards 0. It's only when those 2 points essentially merge that it becomes the tangent line. We can look at this as x varies as well. This is more complicated. Now I fixed delta x to be 0.2. Those red dots horizontally are 0.2 units apart. The red dashed line that you see is almost a tangent line. Not quite, but almost. Its slope is technically 2x plus delta x. That's approximately equal to 2x, the derivative. The orange graph is the graph of the derivative. Notice the orange graph has an output of 0 when x is 0, just like the blue graph has a horizontal tangent when x is 0. The orange graph has positive outputs when x is positive, just like the blue graph has positive slopes when x is positive. And the orange graph is negative in value when x is negative, just like the blue graph has negative slopes when x is negative. One more subtle thing, say over here, the derivative is getting bigger and bigger positively, just like the slope of the blue graph is getting higher and higher because it's concave up. That's a lot to try to think about all at once, but if you spend time thinking about it, that would be helpful. All right, change of pace. Logarithms. 15 minutes. Okay, we'll do more logarithms on Friday. Okay. So we're going through the chapter 1 stuff, which is pre-calculus review, very quick. You know, we'd be doing this stuff in pre-calculus over the course of an entire semester. And here we're fitting it into 2 or 3 weeks. Trying to weave in some calculus as we go, even though the official calculus doesn't start until the very end of chapter 1. So we have a variety of topics here. Logarithms, exclamation point. Why do I put an exclamation point? Just because people either really like logarithms or they hate it. But if you hated logarithms in the past, you can try to change your mind. If b is positive and b is not equal to 1, this exponential function is 1 to 1. We've seen exponential functions already, right? A times b to the x. I picked the a to be 1 here to keep it simple. B can't be 1 here because 1 to the x always equals 1. It's not very interesting. It's just a horizontal line. That's why we don't let b to the 1. We don't let b to be negative either because that just gets weird. Like, what's negative 3 to the pi power? Negative b's would be weird. Okay? So we avoid negative b's. What's the range or image of the function? All positive outputs, right? You already knew that. We talked about this last time, I think. Yeah. B is bigger than 1, the graph looks like this. If B is between 0 and 1, the graph looks like that. Exponential growth versus exponential decay. In either case, the possible outputs are all the positive values along the y-axis, above 0. That's the range, or image. That's another name for that. 0 to infinity, the set of all y where y is positive. Being 1 to 1, it must have an inverse function. It passes the horizontal line test. Being 1 to 1, we talked about last time, means you got an inverse function. It passes the horizontal line test. Every output has exactly one input that goes to it. Every output, like this one, has exactly one input. It's not like a quadratic. What is the inverse function called? It's called log base b, the log base b function. And I'm purposely not swapping the variables here, though I will eventually. I think conceptually speaking, it's good to not swap them at first. That's just its name. There's lots of things in math and science that have certain names that are just weird. Who thought of that name? Logarithm? Logs? What in the world? Well, there's a person named Napier. That's what I thought of. I should probably look into why I call them logs. It might make something interesting. I don't know if anybody knows the answer to that. Log base b, logarithm base b, log sub b of y. Say of y, not times. There's no multiplication going on over here. It's not log times y. It's not log times b. It's not b times y. It's log base b of y. It's a function of y. It's a function that's just got a special name and a special symbol. If b is 10, that's called the common logarithm. And we just typically write log M of b is e, that's called the natural logarithm, and we typically write ln. Just in Mathematica they don't. But b could be any positive number except 1. Here's a picture of the situation when b is 2. So that blue graph is 2 to the x. Given a y, any y that's positive, there's exactly one output that gets mapped to it. And we call that output, or that, there's exactly one input. We call that input log base 2 of y. This is not the graph of log base 2 of y, it's just a way of thinking about it. Actually, that's a little bit of a lie. Chew on this. It actually is the graph of log base 2 of y if you think about it in the right way. And what I'm going to tell you to think about it is get a mirror, look the opposite direction as the picture, look in the mirror with your head sideways, and then you'll see the graph of log base 2 of y with the y-axis looking like it's going to the right. Get a mirror, look the other way, turn your head sideways like this, okay? Then it will look like an ordinary graph of log base 2 of y, with the y-axis looking horizontal based on you turning your head. I'm serious. Do it. It's worth it. I'm serious. Why? I said Siri, did I? Didn't I? Serious. Siri thought I was talking to her. Here's a picture for a fixed. Well, okay. What's changing here? I guess B is changing in the second picture here. And all the point is that you can get a one-to-one graph, no matter what B is as long as it's not equal to 1. Right in the second picture. Why are the following equations true? B to the log base b of y equals y for all y that's positive, and b to the log base b of b to the x equals x for all x. You've probably seen those equations before. Why are they true? By the way, it is helpful to think about particular examples. Just haven't yet. Log base, what's log base 2 of 8? 3. Why? Because 3 is the number you got to raise 2 to get 8. The equivalent exponential equation is that. X is like the 3, 8 is like the y. These mean the same thing, equivalent. But why are these equations true in general? I asked you for a reason. It has to do with composing these things, a function and its inverse. What happens when you compose them? Like this. What do you get? Why? Right? They undo each other. Write that equation in terms of logarithms. F inverse of y is log base b of y. I plug that expression into f in place of the x, I'm going to get b to the log base b of y equals y. It's because they're inverse functions. Y has to be positive to be in the domain of the logarithm. The other one is for the other composition. F inverse compose f of x is f inverse of f of x, f inverse of b to the x better equal x. It will equal x because f inverse is the inverse of that. But what does this mean? Well, what's the inverse function? It's log base b of y. Plug in b to the x in place of y right there. This is equivalent to log base b of b to the x equals x. They're inverse functions. They undo each other. That's why these equations are true by definition. they are true. But they are confusing. So you have to think real clearly about them. More on logarithms. An alternative way to think about the log-based b of y, maybe this is what you're, whenever you first learned about logarithms, 10th or 11th grade or something, what your teacher probably said is log-based b of y is the number to which b must be raised to get y. Just like that, that's the definition. The number that b must be raised to get y. That might have been what your teacher said. When b is bigger than 1, the usual case, what does the graph look like? It looks like this. And it is, now I'm going back to using x as the independent variable. Now I've swapped the variables, so that when I graph them in the same picture with the independent axis being horizontal, I get the reflection power. So here's the graph of y equals 2 to the x, here's the graph of log base 2 of x. There are reflections across this green line that y equals x. And these dots have opposite coordinates. This is 2, 4, that's 4, 2. They're reflections, they're symmetric if you turn your head at a 45-degree angle like that. Mirror images. The graph of any log base b of x when b is bigger than 1 looks like this kind of shape. Increasing, concave down. Looks like part of a strange-looking frown. It's got a vertical asymptote as x approaches 0 from the right. And it does keep going up forever and ever. Actually, the limit as x goes to infinity is infinity. This does go up forever and ever, higher than any horizontal line, but very, very slowly. It does not have a horizontal asymptote. But it takes a while to get above any horizontal line. Like a million. You know how long it would take to get above a million? X would have to be bigger than 2 to the millionth power for this graph to get above a million. You know how big 2 to the millionth power is? It's bigger than a Google. Way bigger. Okay, and a Google is bigger than the number of atoms in the observable universe. So we're talking way out there. I think this is our last slide. Yeah, okay. Then we're done for the day. Besides the defining properties of logs, the following fundamental facts are true with the usual conditions on b. b is positive and not equal to 1. Log base b of capital A times capital B is log base b of capital A plus log base b of capital B. Maybe I should use C and D instead of B. I use capital letters, so it's okay. Log base b of capital A divided by capital B is log base b of A minus log base b of capital B. And finally, log base b of capital A to the p power, p for power. The power can be brought in front. It's p times log base b of A. A must be positive, but p can actually be anything. It can be a negative number. You've seen these before. You may not remember them, but you have seen them before if you're in here. You may not have ever understood them. You got to work at it, okay? One way to try to understand them is to think about examples. That's the initial best way to start thinking about them. Take log base 10 of 1,000 times 10,000. 1,000 times 10,000 is 10 to the third times 10 to the fourth, which is 10 to the seventh, 10 million. This is log base 10, common log. What do I need to raise 10 to get 10 to the seventh? I need to raise it to the seventh power. This is 7. That equals the sum, log base 10 of 1,000 plus log base 10 of 10,000. It equals 3 plus 4. That's also 7. So thinking about examples is helpful. Examples are not proofs, however. On Friday, we will prove at least one or two of these. This is one place in the class where we do some proofs. You should be able to prove these for exam 1. That's possible, and you might put a proof of them on exam 1. So it is worth your while to think about. But this is the initial way to help you make sense of it. Try other examples as well. Okay? Have a good day.